heterogeneity is related with any of the explanatory variable included into the model. In that case, you use fixed effect model. If you find that that variable is not related with any of the explanatory variable, then in that case we may use random effect model. So in a correlation case, you use fixed effect, and non-correlation case, we use random effect. So let's suppose in a scenario that unobserved heterogeneity is correlated with any of the explanatory variable. So given that true model is fixed effect model, but if we use random effect instead of using fixed effect, in that case we get bias and inconsistent estimate. But vice versa is not true. Let's suppose that true model is random effect model, and if we use fixed effect model, so in that case we will get consistent estimates. But in a case when true model is fixed and we are using random effect, in that case we get bias and inconsistent estimates, always remember. So question arises, how do we choose or how do we decide whether unobserved heterogeneity is related with any of the explanatory variable? Is there any guiding principle for each? So the answer of all these, yes. There are guiding principles which guide us for choosing between random effect model and fixed effect model, and we will study about those guiding principles in this section. So before moving those guiding principles, let's talk about the characteristics of this time invariant unobserved variable and how it affects our model. And for that, let's assume P is a random unobserved heterogeneity variable and Y and X are observable random variable. So we are assuming that C, which one is a you can say constant. So since you are assuming that that unobserved variable one is time invariant, okay, you're not going to change over a period of time. So that's why I assume that written here C, and Y and X are as usual are dependent and independent variable. X contains all the X is a matrix here, and Y and X are observable random variable here. So unobservable random variable is C only here. So the vector of interest in our case is Y, X1 to Xk and C. Further, you are going to assume that you are going to deal with a linear regression model. So C is entering into the model additively like this, and our objective is to calculate beta. So given that regression model satisfy all assumption of classical linear regression model, if C is uncorrelated with explanatory variable, in that case we will get consistent and unbiased and consistent estimates of all parameters. If that is not the case, then regression model suffer with the endogeneity problem, and solution of endogeneity problem in a cross-sectional data case, we know either you use proxy variable or we look for a instrument variable, and these things we have done in our EDO course. In a panel data case, uh, there are some other possibility arises, and so to understand that, let's assume that y and x are observed for two different time periods. Let's say t equal to 1 and t equal to 3. And if going with the assumption that c is time constant. So given that expected value of y given x and c become this I am talking about. So, so this one is our regression equation. So this one is expected regression equation. So without the error term. So this one is the expected value of y given x given c, and further x t be defined in this way. And since c is a constant, so you are assuming that the coefficient of c equal to 1. So full regression equation becomes this one. This one. So now here you are having two constants. The one is the beta 0, and the another one is c. Okay. And this one is our error term, and this one is the explanatory variable. So since this one is unobserved variable, so this become part of this error term. So the composite error term become here Vt. But before that, if you will talk about this error term, which one is the Ut, so assuming that the Ut is not correlated with any of the explanative variable given C, so you can write that expected value of U2 given xt c equal to 0. And if you also assume that expected value of xt c equal to 0, so there is a difference between this and 2. So this one is assuming that there is no correlation between explanative variable and you can say ut. And here you are assuming that again there is no correlation between explanative variable and unobserved cross-sectional heterogeneity, which one is represented here C. So given that these two assumptions satisfy, we can use full OLS regression. But what if this one is not? So if this is the case, where unobserved heterogeneity one is related with the one of the explanative variable, so in this case we need to think some other method. So with the 2 layer of data, so there is a one possibility that we can eliminate time constant unobservable c variable by taking a difference. So difference is here. So this one is the delta y equal to y2 minus 1. So when we subtract previous, you can say the year value with the current year value, you can get the first difference. So this one is the first difference. So we'll take a first difference of each variable, including error term. So if you do that, we'll end up with this equation. Which one is delta y equal to delta xt plus delta u. So by taking a difference, we got eliminated. So end up with this regression equation. And here you can use OLS to estimate the value of parameter. And using OLS is here same as like we do, you use OLS in case of cross-sectional data set. Because with the two time period case, when t equal to 2, one period got eliminated, so we left with only one period, and that one is equivalent to the cross-sectional data set. And again, given that all assumptions of cross-sectional regression model satisfy, what we will get unbiased and consistent estimates of parameter. So the key condition for OLS for consistently estimating the beta is orthogonality condition. So orthogonality case, we know there should be no relationship between error term and explanatory variable. So if this error term, which one is the new error term or first difference error term, you can say if this one is not correlated with this one, in that case OLS apply, and applying OLS we get unbiased and inconsistent estimate. So these are the assumptions. If this satisfy, if this this satisfy, which one is the rank condition, again the essential condition for getting unique estimates of each coefficient. So if these two satisfy, we get unbiased and inconsistent estimates. But let's explore this condition further. So since this one is the delta x prime delta u equal to 0, so when we expand these terms, we will write this term as like this. And expanding further, what we will get? We will get this equation. So this one becomes 0 by assumption. This one becomes 0 by assumption. But what about this term? Where we are talking about the correlation between uh, error term of second time period with the explanatory variable of first time period. So since t equal to 1 and 2 here, so 2 represents second time period, 1 represents first time period. So what about this? Whether this should be equal to 0 or not? So the logic, the argument is here, it may not equal to 0. But if you go with the assumption that this one is also equal to 0, this one is also equal to 0, and together these along with these reflected through this assumption. So if this satisfies, that means we are assuming that this one equal to 0, which may not equal to 0, OLS gave us consistent estimate. So this one is just for illustrative purpose for you, just to show this thing. Okay. Because when T1 is greater than 2, so in that case, there is a possibility that you may not get this one equal to 0. That means the error term of second time period related with the explanatory variable with the first time period, or in general we can say error term of any other time period related with the error term of other time period. So when we assume that the error term is uncorrelated with the x1 and x2, that means any time period of explanatory variable. So that one is the condition of strict exogeneity condition. So that one is a condition of strict exogeneity condition, and we can interpret strict exogeneity in the sense that the error term is not related with the either current, past, or future value of explanatory variable. So if that satisfies, that means we are assuming strict exogeneity assumption, and assuming that we can apply OLS to estimate the value of parameter. Now let's move on to the second assumption. Which one is this one? Rank of expected value of delta x prime delta k equal to k. So it also requires some attention, and That is because of, let's suppose that X contains time constant variable as like sex, religion. So given that X contains time constant variable, if you take a first difference, so in that case that variable disappears from the data set. So delta X becomes 0. And in that case, the second condition may not satisfy. So this means that we can't, if you go with the second difference, we can't get the estimates of sex, religion, or we get the estimates of impact of sex, religion on explanatory variable. That also means we can't distinguish the impact of sex and religion from unobserved cross-sectional heterogeneity. So, so two cases are here. First, we can't get the estimates of sex religion if we go with the first difference method, and that one is because of we can't distinguish or disentangle the effect of C with the other time constant variable. So effect of all sex, religion, and other time constant variable basically converge with the C variable. So after running a regression, whatever value we will get, that one is C, and that includes the effect of all time constant variable. And all other variable which having some degree of variation over a period of time, we get the estimates of those variables. So now let's consider a case when you have more than two time periods, say t equal to 1 to 10, and further assume that panel data is balanced and short panel. Balance means we do not have any missing observation. Short means we are having n substantially greater than t. So for example, n 1000 and t 10. Short panel can't be case when you are having n 50 and t 48. So this can't be called a short panel, despite that n is greater than t. Short panel in a strict sense, n is substantially greater than t. In case of unbalanced, okay, though we use, I mean, most of the concept we use in case of balanced panel, but apart from that, unbalanced panel require formal description of why data is unbalanced and some selection issues. Uh, Reference reading for this one is Cameron and Trivedi book, where you will find a substantial discussion on panel data and particularly this sample selection issue. Though whoever have interest to have more information on these two issues may refer that book. Otherwise, unbalanced panel data and sample and relating sample issues, sample selection issues are not part of this course. Both of the things are part of the CSPD2 course, okay, but not part of this course. So, assuming short panel, and in the logic behind the assuming short panel, one is this, is that asymptotic analysis is valid even for arbitrary time dependence and distributional heterogeneity across T. So this statement is important because here you are having a time dimension, and as I told, when T is greater than n, then in that case we apply the techniques of time series econometric. But even when n is greater than T or substantially greater than T, there is some time dependence, though that those time dependence are arbitrary, and there is a heterogeneity across T. So when we go with the short panel, so so in that case, asymptotic analysis, the properties of asymptotic pro, as, sorry properties of asymptotic properties apply, and that take care of the time dependence and cross sectional heterogeneity across T. And that's why it is written here. It is important to note that asymptotic analysis provide a reasonable approximation to the finite sample properties of estimator and statistics. And this thing we have already done in a previous course. So, so same thing is written here. The third case is when T is at same order. As I told you, when n equal to 50 and T equal to 48. So in this particular case, we do not have much information how actually we'll deal with this, whether we apply one, whether we deal with this as a short panel or this as a long panel. So I think more research need to be done in this particular case. Otherwise, when n is n is greater than T, we go with the short panel. And in the mechanics of short panel, and when n is T is greater than n, we use time series econometrics in dealing with the panel data regression model. That means in that case, we bother about the stationarity, non-stationarity, and other dynamics of time series econometrics. So, so in this course, we are strictly considering only short and valence panel. So, as I told you, there are two methods: random effect method and fixed effect method. I interchangeably use random effect with random effect model. So random effect model means you are going to use random effect, or you have used random effect. Fixed effect model means fixed effect model is used for the analysis of panel data regression model. So otherwise, uh, these two called a method: random effect method and fixed effect method. And choice between these two methods depend upon C, whether C is correlated with any of the exponential variable or not. If C is correlated, then you can use fixed effect, otherwise you use random effect. So we are assuming that C is not correlated with explanative variable, so random effect model or random effect method apply. So we are going to discuss that first. After discussing the random effect method, we will discuss fixed effect method. By the way, any doubt till now? Okay. So, so let's start with the random effect model. So, so we can write the random effect model as like this. So as like the full regression model. So, and here I have included unobserved heterogeneity variable. That one is C. I represent because that unobserved variable varies across the cross-sectional unit, but remain constant over a period of time. That's why T component is missing from Ci and UIT. And as I told you, Ci as Ci is unobserved, so this become a part of the error term. So this become a composite error term. So VIT equal to Ci plus UIT. The assumptions of random effect model are these. So the first assumption one, the expected value of UIT given XIC equal to 0. And the second assumption was expected value of Ci given Xi equal to 0. Why we required to assume these two assumptions? Because assuming that Ci is not correlated with any of the explanative variable. So given that, since this one is the error term, another error term, so first we need to make an assumptions regarding these, then assumptions regarding these, then you make a combined assumptions regarding VIT. So, so first assumption implies that Xi is not related with the error term. Second one is Ci is independent from Xi. That means Ci is random and not correlated with any of the explanatory variable. So satisfying assumptions 1A and 1B further imply that expected value of composite error term given Xi equal to 0. Assumption 2-1 is the rank uh, assumption. So the rank of expected value of X prime Xi prime omega inverse Xi equal to K. So now the new things comes here. That one is the omega. In a pooled regression case, we do not bother about this omega thing, but here we are bringing this omega things here, and omega is nothing else. This one is the expected value of Vi prime, which one is the composite error term. An expected value of since this one is our stochastic error term in the original regression equation, the expected value of Ui square is sigma square U, which one is the variance of error term, is like this. We are assuming no autocorrelation case as we assumed in a pooled case. So this, but since now we are having a composite error term, which one is the VIT, and VIT includes Ci. So if you calculate the expected value of VIT square, then we will get this term. The expected value of Ci square, expected value of UIT square, and 2 into expected value of Ci UIT. So since this one is the constant, okay, and it constant for each cross-sectional unit, but it varies over period of time, so it has a variance of sigma square C. This one is the variance of stochastic error term, so this one is sigma square. And again, if you, from the assumptions one, which assume that error term and explanative variable given C is not related with one another. So this one equal to 0, this one equal to 0. If you go with the assumption, then this one equal to 0. So then Ci Ui also not related with one another. So look, again I am saying if Xi is not related with Ui, Ci is not related with Xi, then Ci is not related with Ui also. So, so this one is also equal to 0. So that means expected value of VIT square equal to expected value of CI square plus expected value of UIT square, which one is sigma square C plus sigma square U. Since in a random effect case, you are assuming more assumption as compared to the full regression model assumptions. So the question arises, why we need more restricted assumptions than needed for a full OLS case. So the answer of that lies in this composite error term. In a, and also in a full regression case, we assume that there is no correlation between UT and XS when T not equal to S. And even when T equal to S. So this one is the full assumption. So the covariance between U2 and XT equal to 0, you can say, without specifying these things. Okay. The same we are assuming here also in a panel regression case also. So it's, but since CI, which one is a unobserved cross-sectional heterogeneity, it's part of the error term. And this, I think, further I have elaborated that. So let's suppose that if I say, let me open the whiteboard. So let's suppose that if I write a regression equation, y it equal to beta 1 plus beta 2, x2 it plus beta 3, x3 it plus uit plus uit, and including C, beta 1 plus beta 2, x2 it plus this one also beta 3, x3 it plus Ci plus uit. So this one in a panel case, in a random effect case, VIT. So if we talked about the autocorrelation thing, autocorrelation, so even in a pooled case, if we go with the assumption that there is just some degree of or there is a autocorrelation, so that means ut is related with ut minus 1. So this one is the first order autocorrelation. You may move on to the higher order autocorrelation u2 minus t, u2 related with the ut minus s. So this one is autoregression 1 case, this one is the autoregression 2 case, and this one is the autoregression, let's suppose a row case. So what is the solution of this autocorrelation? Either you use GLS and FGLS. That one is the solution. Even in a case of pool, we have done, even in a case of OLS with the cross-sectional regression equation case. Are you able to recall?
Yes, sir.
Okay. So the thing I am trying to say, in a presence of autocorrelation in OLS case, you use either GLS or FGLS and get the consistent estimate. But there one assumption is this: the degree of correlation between the error terms, okay, and it vanishes over a period of time. That means when we will talking about the correlation between ut and ut minus rho, okay, that means here the degree of correlation between these two error is almost 0 as compared to the correlation between ut and ut minus 1. Are you getting me?
Sir, I didn't understand why the UT and UT minus P there is no correlation, whereas the UT and UT minus 1 there will be
Because
correlation. I didn't understand.
this one is light apart from this. Let's suppose that your disturbance occurred at point T. So that disturbance might have any greater association with the next time period, or having a more impact on the next time period as compared to the time period apart from apart away from, or you can apart from T. So when you move further away from one point to another point, let's suppose that this one is the time scale, this one is the a time period when disturbance occurred, and this one is lies further away from this one. So the impact of that disturbance declined over a period of time, and at a one point it become vanished, it becomes zero. So the impact become impact vanished. So that the reason when we look a correlation between the error term u2 and the current error term with the error term which lies far away from the current error term on a time scale. So we will get a uh, either no correlation or very low degree of correlation.
Okay, sir.
Okay, so if I write a regression, let's suppose that you take which one is the, here I say, here I have written row. Let's use any other. So let's suppose that delta ut minus 1 plus epsilon t. So this one is the AR1. If given that this absolute value of rho less than equal to 1, when we go further away from T, okay, so the effect of any disturbance that occurred at point T vanishes, and it vanished. So, so given, so that one is in a case of full regression case, or you can say the cross regression case when you apply OLS. But in a random effect case, since CI effect and CI is part of VIT, so we never get a case like this where the correlations entirely vanish, even when we are considering the correlation between two distant time periods. Because of this unobserved, because of this C thing. So even though you can say the correlations never vanished, okay, and you always find some degree of correlation between the error term and correlation between the error term, which we call autocorrelation. Okay, we can apply GLS and FGLS as usual we do in case of OLS. And because of that reason, instead of you can say using ALS, you use FGLS to get the consistent estimates of parameter. Second thing is that assuming strict heterogeneity, if you uh, look the expected value of VIT square, which one is this one? That one is actually the error of variance of composite error. Then variance of constant term is given there, and given that T not equal to S, when we uh, see the covariance between uh, two error terms, so we will get that one is as sigma square C. So the variance one is this one. Variance one is this one, no doubt. Variance of composite error term. Which one is the variance of constant plus variance of stochastic error term. Variance of constant is this one. But if you talk about the covariance of composite error term, so that covariance equal to the variance of unobserved variable, and that you are getting after expanding this one. So this one is ci square. This becomes ci uis. So we have assumed that there is no correlation between ui and ci. So this becomes 0. So this becomes 0, and this also becomes 0. So covariance becomes this one. And this one is the correlation, which I were talking about. You always get some degree of correlations between the error terms, irrespective of how apart two period are. So t and s, it doesn't matter whether t is near to s or very far away from s. You always get some degree of correlation between that two, and that one is a sigma square c divided by sigma square. And also here you can say you always get a constant correlation between error terms. So this one is the constant, this one is the constant, this one is the constant. So overall this term become constant. And since this one is the composite error term, we are talking about the correlation between the composite error term. So you must ensure that this row less than equal to 1. In OLS case, of course. In a panel case, as I told, this one is not. Sorry. We ensure that this should be less than 1. Otherwise, that one is the case of non-stationarity, and in a non-stationarity case, we get spurious regression result. So that one is the part of time series component, but ensuring that this row value less than equal to 1. Okay. It vanishes when it goes very far away, and when you consider that two distant time period, and lesser the row value, the convergence achieved quickly. Okay. But as I told you, in a panel case, because of that convergence in C, this often not possible. So going with our, irrespective of how distant period you are considering, you always get some degree of correlation between the error term. Third assumption one is here. Expected value of ui prime given xi, ci equal to sigma square u. Which one is the assumption of, you can say, constant variance assumptions of error term. And the next one is the constant variance assumption of unobserved variable. And if this satisfied, we get unbiased and consistent estimates of parameters. So for testing the presence of unobserved effect, so there is a test which called a Bruce-Pagan-Lagrange multiplier test. So I am not going to algebraical detail of that test. Okay, we will apply this test when we will do the practical exercise relating with the panel data. So next one is the fixed effect model that will start from next lecture. And as I told you, you use fixed effect when error term is unobserved variable, or we can say unobserved cross-sectional heterogeneity is correlated with the any of the explanative variable. This thing you need to understand. Okay. So this thing I were talking about basically in a general usual time series setting, we generally assume that error terms which are generally quite apart from are not or slightly correlated with the one another. But in a panel data case, it is often not true due to presence of CI. And because of that reason, the panel is an random effect estimate based on GLS or FGLS instead of simply considering OLS case. Because in OLS case, you may get a correlation or not, but in a random case, you always get a autocorrelation problem. So serial correlation is you can say the inherent part of uh, random effect model, and that one is because of presence of unobserved variable into the model. So you always get this one, this error term. So always get a positive correlation between the error term, and because of that you use FGLS. Always remember this. Any doubt? Uh, Sudhit asked heterogeneity in what? Error variance? No, not in error variance. Heterogeneity across the cross section in general. So when you are talking about the unobserved variable, that that means that also means unobserved cross sectional heterogeneity.
Sir, could you explain that unobserved cross-sectional heterogeneity means?
Uh, as I told you, we are dealing with the cross sectional and time series. So you are having a multiple information for a single cross sectional unit, right?
Yes.
So so uh, uh, the same you are having for each cross sectional unit. So
Yeah.
you can't go with the assumption of the all cross sectional unit are homogeneous.
Okay.
There
Okay.
must be some heterogeneity across the cross sectional unit.
Okay. All right.
And unobserved I means ki whatever the heterogeneity uh, present between the cross sectional unit that are not directly observed to us, like
Okay.
something ability we can't observe directly.
Okay.
It's something related with the gender thing. Okay, it might be the women are more efficient manager as compared to the men in general. Okay,
Okay.
but we can't observe that one.
All right.
That may related with the customs, culture, like this. Like I'm giving you one example. When we look the meat consumption data, okay,
Okay.
so Indian on average consume less meat as compared to American. Okay, so
Okay.
that one somewhere related with the.
Culture.
Of
Okay.
course, when you diagnose, you will get some reason, but those reasons are not. We can say the fully explained why American eat more as compared to Indian.
Okay.
So that's the reason.
All right. Okay. Thank you, sir.
Okay. Any other doubt? Have you started reading? I'm stopping.